Collisions are 2D by its bidimensional effects, but, in themselves, they are one-dimensional. Everything happens along the one line of action. So, we can take advantage from what we learned before. Before collision, bodies A and B approach each other. Consider the components of their initial velocities. Unit vectors, E and U, are of utmost importance. Everything happens along the direction of unit vector E. After collision, bodies go away from each other. Components along the direction of unit vector U do not change. VE and VBE will change in accordance with a 1D collision, which happens along the line of action, the direction of unit vector E. So the change from the initial to the final velocities of bodies A and B is due to the change in their components along the line of collision, the line of action. Please observe and understand the lettering, so you won't get lost along the way. These are the steps needed to solve any 2D collision. You will learn how to proceed in the following. First, find the angle of attack and define the unit vectors in accordance. Find the components of the initial velocities, along the directions of the unit vectors, U and E. Apply the equations for the 1D collision to the component of the velocities along the direction of unit vector E. At last, add the two components of the final velocities.
Remember, the component of a vector, along any direction, is given by the dot product of the vector and of a unit vector, along that direction. The dot product can be calculated without reference to the angle, as the sum of the product of the corresponding components of the two vectors. The dot product allows to easily calculate the component of a vector, along any direction. First, we have to find the components of the initial velocities, VA and VB, and of the unit vectors, U and E, along the x and y axes in order to proceed, operating the necessary dot products. Remember how to define a vector, from its magnitude and the angle of its direction with the x-axis. Our unit vectors are perpendicular and can be defined just by the angle delta. We describe the initial velocities by its magnitude and the angle they define with the x-axis. Just as the unit vectors are defined, we, now, operate dot products in order to find the components of the velocities along the direction of the unit vectors, E and U. Notice the use of known trigonometric identities.
During the collision, the components of the velocities, along the unit vector E, are changed according to the known equations of the general 1D collision. Via E changes to VE final, and VBE changes to VBE final. Just replace VA by VAE, and VB by VBE in the known equations for the 1D collision. Now, we have components of the final velocities, VA, final, and VB, final. But these components are according to the directions of the unit vector u and of the unit vector e, not relative to two our x and y axes. In order to have the components of VA final and VB final, according to the axes x and y, we recall the components of u and e on axis x and axis y. Multiplying the unit vectors by scalars, and adding the corresponding components, we have the coordinates of the final velocities of both bodies, after collision, in the x and y axes. We have all we need. We just solved the problem of the general 2D collision.
Let's use the formulas we just learned. Find the magnitude and the angle with the x-axis of the velocities, VA final, and VB final, of bodies A and B, after collision. In the drawing, you have all the information you need. The coefficient of restitution is E equals 0.8. Remember that E and U are unit vectors. We use them for distinguishing, for each initial velocity, the component which will not be affected by the collision, from the component which changes with collision. Apply formulas. It's time for calculating the components in the x and y axes. Now you have it all. In order to have the visual feeling of the final velocity vectors, we need to find its magnitude and angle, with the axis, x. We know this from middle school. And this. But, please, note, The function arctangent would give two different values in the interval of our interest, between 0 and 2 pi. So, we need to use more information to determine the angle of the vector velocity. For that, we resort to the positive or negative sign of the y component of the vector. Its velocity, up, or velocity, down. So, the calculator is not enough, in this matter of facts. The components of the final velocities of bodies A and B give us all the information we need about them. Let's find their magnitude and direction. Note the need of using the sign of the y component of velocities to choose the right angle they define with the x-axis. Now, we can draw the vectors. Compare velocities, before and after collision. The scaled drawing testify that the components perpendicular to the line of action did not change. Verify the conservation of momentum over the line of action. This is a simulation of the situation we have been calculating. The velocity of the center of mass of the isolated system of the two bodies does not change with the collision. This is a consequence of the conservation of momentum.
We consider, only, the easier case of two homogeneous spheres. The center of mass is, also, the geometric center. After detecting collision, we find the angle of action or of attack. At first we notice two known possibilities. There are two angles with the same tangent value. You can choose, blindly, any. The choice of delta, as angle of collision, will lead to a system of unit vectors. The choice of delta minus pi will lead to another system of unit vectors. Both systems can do the business, as they are just a necessary tool. If you need to build a simulation software, you need to find the magnitude, VA, and VB, and angle, alpha and beta, of the velocities, just before collision. To find the velocities, is easy. Just consider two positions of the ball, at collision and, the other position, just before collision. The distance traveled by the body is proportional to the velocity, in a given time. We resort, again, to the arctangent for finding the angle of the velocity. However, the arctangent gives the same result for these two very different situations. You can distinguish between the two situations, for the same value of the tangent of different angles, observing the change in the value of the y-coordinate.
Solve this easy problem. Find 1. The velocity of the ball m if the two positions are separated by 0.1 seconds. 2. The angle, mu, the velocity of the ball does with the x-axis, before the collision. 3. Both balls have the same radius, r. Find its value. 4. The angle of attack, delta. Solve, before view the solution. The angle of action is defined by the two centers of mass. You are free to choose the angle given by the calculator, or add pi to it, in order to adopt a positive value. Hope these series of videos, about collisions, have been of some help for you. We will keep improving its readability.